right, we're on our third lecture pertaining to the transmission electron microscope. So I've aptly called this lecture TEM number 3. What we have here is a kind of a collage of images, and this is an optical micrograph. So this is combining the information you would get from light optical microscopy with that of transmission electron microscopy. And maybe it's not the best figure I've ever made, but it was kind of showing schematically what kind of microstructures you get at different intervals away from the crater surface. So this is the edge of an impact crater surface. You see all these kind of interesting microstructural features, and you see stuff here. And here you have heavily dynamically recrystallized grains. Here you see microbands, and here you again see microbands, but they have a slightly different morphology and they're somewhat bigger. And then further away from the crater surface, you get dislocation cells. And dislocation cells are kind of like grains, actually, and actually do contribute to the strength of a material. So you can modify the Hall-Petch equation and add a term for dislocation cell diameter and kind of estimate the effect of the presence of these dislocations or dislocation cells on the overall yield strength. It's a very interesting phenomena. There was a time where I was involved in a project. It was dealing with titanium, and you had two data sets basically, and they had pretty much the same grain size, but one data set had drastically different yield strength, and we did some TEM and found that there was more dislocations basically in the sample set with higher yield strength. Anyway, this is kind of a story of a battle, and it was with an individual that didn't really believe in the power of TEM data because this person believed that it wasn't statistically significant. So I kind of say these little stories to students because you never know what mindset people have that you interact with. Anyway, back to TEM. So we have an example TEM schematic. So I've shown this, I think this is the third time I've shown this in this lecture series. Got this off of MyScope. And what's kind of cool is if you think about it, and I've said this before, TEM is basically a big projector. And you have your little specimen, the beam goes down, and you have your transmitted beam and your diffracted beam. And this particular model is showing an indication of something called a projector lens, which is kind of interesting. And so kind of going into the concept that you're really projecting the image of the microstructure onto this, it's usually a fluorescent screen or phosphorescent screen. The fact that a TEM is pretty much a projection system kind of is the basis for this concept here called camera constant. And understanding the camera constant for your instrument is extremely, extremely huge because it allows you to basically interpret diffraction patterns. You can also tell if your system is calibrated or not, so if you can trust the data coming off your instrument. And the concept of camera constant, it's RD equals lambda L, and lambda L is your camera constant, and lambda is wavelength and L is camera length. Okay, so this is the wavelength of your electron beam, and this is the camera length. And the camera length is the distance between your specimen to the recording plane. And R is physically measured from the diffraction patterns, and G you can get from similar triangles basically, and you can also calculate the magnitude basically of your K vector also off of similar triangles. And we can work that out right now. Let me just kind of read the bullets and then we'll kind of actually physically work this out. So this comes about as a reduction of Bragg's law, and I'll kind of show that later. The electron diffraction angles are much smaller than X-ray angles, so that's kind of just put that putting that out there. We're at a smaller wavelength, so if we're dealing with Bragg's law, we're going to be having a very small theta, basically, as compared to an X-ray diffraction. We don't really work with theta that much with TEM diffraction pattern interpretation, if you will. I'm going to go through this derivation. It's explained by similar triangles. It's very simple. We'll see it right now. RD equals lambda L is kind of an equation that comes into play when we're interpreting diffraction patterns, and we'll see that later in this lecture. And the units of camera constant are angstroms centimeter, and we'll kind of see that as we use it in play. So let's go and work out this camera constant calculation. Alrighty, so we have camera constant, and it's just a matter of similar triangles, and so we can kind of write it out like this. So similar triangles, L over R, which is this first triangle we have, and so I can kind of redraw it over here. And then we have our little baby triangle here, which is K and G. So we can say L over R equals K over G equals 1 over lambda over 1 over D. And so we can rewrite now L over R equals D over lambda, because of how, you know, this goes down and this actually kind of goes up because you're dividing by a divider. And lambda L equals RD. So nothing to it, really. Lambda L is in angstroms centimeters, because camera length is measured in centimeters and R is also measured in centimeters. And historically, we've measured wavelength and D-spacing in angstroms, not nanometers. So that's where this unit comes from. Hopefully this is helpful. All right, so we've worked out the camera constant. This is just kind of showing it actually does satisfy Bragg's law, and I kind of worked it out a little bit. So we have 2 times the k vector sine theta equals the reciprocal lattice vector. Based on that, this is when diffraction's occurring, basically. And so we said when the k vector, and I probably should have put it over here because I have the g vector going here. So this is also k. So when the k vector meets the g vector, we get a diffraction spot. I was kind of saying an angel gets its wings as a joke, but we get a diffraction. We get a diffraction spot. Kind of seeing the camera constant slide again. So how do we use this in a practical sense? So indexing patterns is a very big use of the camera constant. So we have our copper with a lattice parameter of 3.61 angstroms, and we have our 300 kilovolt accelerating voltage, and we measure the first spot is seen below, 1.2 centimeters, measured physically off of a diffraction pattern. Okay, so I had a ruler and I printed it out. That's basically how I would get that. Or I had it in some digital imaging software and I measured it digitally. Maybe that's more precise. I know the camera length of my instrument to be 113.8 centimeters, and camera length is kind of a static thing, and it's actually set when the machine is set up and calibrated. So I know this camera length. And let's go through the question here, what we're trying to answer, and I'll go through it right now, is which spot is this? Oh, okay, so now we're indexing. Okay, so if you remember on XRD, we had diffraction spectra. Okay, so let me try to see if I can make it look kind of cool. This is going to not look that great. I'm so sorry, but I'll try to draw it a little better. And I'm almost embarrassed at myself. So we had 2 theta, and then we had intensity, and then we had some spectra. You know, boom, a peak, boom, a peak. Okay, and so when we were talking about XRD, we were asking, well, which peak is this? Okay, well now here on electron diffraction patterns, the spots are analogous to the peaks. Okay, so instead of asking what peak is this, we're asking which spot is this. And if it's the first reflection, it could very well be 111, 110, or 001. Talking family of planes here. And let's kind of go through this. We'll go through it, and then we'll kind of look at it one more time. So let's go through this particular question asking which spot is this. All right, so we're looking at indexing this pattern here. And so we already know what we're looking at, and I've said it before, I will say it. That's nice to know. That if you are doing TEM and you've gotten to the point where you've put a specimen in a machine and you're seeing diffraction patterns, you probably know what you're looking at. So this is a safe assumption that we know we're looking at what we're looking at here, and had a pen difficulty. So we know our A, little typo there, is 3.61 angstroms, because we know we're looking at copper, because we had to etch it to electrojet polish etch it to make our specimen. So we know what we're looking at. So 3.61 angstroms. This is a diffraction pattern. We measured this R to be 1.2 centimeters, and we have 300 kilovolts of accelerating potential. We know our camera length L is 3.8 centimeters. Okay, so we want to find out some things here. So we want to index it. So usually, what do we know about reflected planes? Well, they have a D spacing. So D spacing. So reflected planes are each going to have their own D spacing. And so that's going to be how we're going to figure out how we figure this spot. So we're going to figure out our D spacing. So in the past, we used Bragg's law for D spacing, right? So in the past, we used lambda equals 2d sine theta, and we knew this because XRD, it was static, 1.54 angstroms. We measured this, so we calculated this with Bragg's law. Now, and I don't want to give away the punchline here. Watching me fiddle with my tablet. Sorry about that, guys. Now we're going to use this new equation for TEM. So this is XRD. For TEM, we use RD equals lambda L, and we're going to solve for D. And so we already have R, and that was, what was it, 1.2 centimeters. And we have L, because that was our machine set at L, or has a set L, so 113.8 centimeters. And we know that lambda L is angstroms. So we need something on the order of angstroms, right? So D spacing is on the order of angstroms, and wavelength is going to be on the order of angstroms. And here, so if you had eagle eyes, you'll see what I was kind of hiding here, and it was this. So we want to use our camera constant, which I've written above, but we need to calculate wavelength. So that ends up being an unknown for us. So we want to calculate our wavelength so we can solve for D. And there's that table you have in the back of the book that tells you for given accelerating voltages, you have wavelength. Excuse me, I forgot what I was trying to get out of my mouth. For given accelerating voltages, you have a given wavelength. You could, if you don't have that table, you can calculate it using that long equation, or you can use these two. I'm going to kind of introduce these equations for approximation for you. So you have one. We kind of talked about it. Lambda equals hc over the square root of voltage. Here, voltage is 300,000 volts. Hc is roughly equal to 12.4, so that's Planck's constant times the speed of light, and I get 0.0226 angstroms. Another approximation is lambda equals the square root of 150 over v, and don't really know the origin of these approximations, or this particular one. This one's a little more straightforward. And I got 0.0223 angstroms, and that's actually pretty darn close, and so we can compare it to the table here in a little bit to see if our approximations work pretty well. But we can continue working through here. And so RD equals lambda L. And so D equals lambda L over R. And so D is going to equal, I'm not going to use that last significant figure. I'm just going to reduce it to 0.022, 0.022 angstroms times, we said it was, 113.8 centimeters. And our measured R from our diffraction pattern was 1.2 centimeters. So we measured our R to be 1.2 centimeters. And, excuse me, I canceled the number out. The units are going to cancel, so we're going to be left with angstroms. All right, so we're going to be left with angstroms, and that is the that is going to be the unit of our D spacing is going to be angstroms, so we're all good there. And so I got D is equal to 2.08 angstroms. And so now we have our trusty equation. D equals A over the square root of h squared plus k squared plus l squared. We're going to assume that this is, it's not an actual diffraction pattern, right? It's something I drew, but we're going to assume this is first order. So we're going to assume first order reflection. And so that means the square root of h squared plus k squared plus l squared is either going to be square root of 3, square root of 2, or the square root of 1. Okay, that's what this is going to be equal to. And we know A, and A was equal to, what was A equal to? 3.61 angstroms. And so D is 2.08. So A is 3.61 angstroms. We know that. And so 3.61 divided by the square root of 3 should equal 2.08 if we're right. If it doesn't equal 2.08, we'll move on to our next spacing. And so 3.61 divided by square root of 3, I got 2.08. So we know now that we're looking at a 111 family of planes by solving it that way. So hopefully this is insightful and helps you approach these kind of problems. Again, the TEM is a projection system. We have our transmitted beam. We have our diffracted beam. And based on the so-called camera setup, we have L, we have R, and then we have wavelength and D spacing. So 1 over L, 1 over wavelength, and 1 over D. Okay, and so we can get LD equals RD, excuse me, RD equals lambda L for our camera constant equation. And we can use that as a starting point to start indexing diffraction patterns using this procedure we've just taken a look at. And if you have any questions, always feel free to ask. Thank you. All right, so we see from our table that our approximation was a little bit off. Keep in mind, this is in nanometers, our approximations in wavelengths. And so we're 0.01968 angstroms. Okay, so 0.001968 nanometers. So in angstroms, we're a power of 10 in the other direction. And we assume 0.022, so a little bit off using the approximation, but that's not too bad. I've pretty much always used the approximation. And anyway, just wanted to kind of show you a little bit in the differences between using the kind of the longer equation versus either a square root of 150 over voltage or 12.4 over voltage. But keep in mind, those are just approximations, but they're really not that far off. Anyway, if it's kind of up to you in the future what you wish to use. All right, so kind of looking at it here, RD equals lambda L. We measured R off the diffraction pattern, so it's 1.2 centimeters D, and we solved for lambda, which is 0.022 angstroms, and we had our L, which was given to us. So we solved for our D spacing. D equals 2.08 angstroms. The spots on the first ring, so I've said it before, it's one of these families, 111, 101, or 100. We can plug it into this equation. We're assuming cubic. In fact, we told us it was copper, so we knew it was the lattice parameter A. One thing I will say, if you've gotten to the point where you're getting diffraction patterns, you pretty much know what you're looking at, because you have to know a lot about your material to make a specimen from your material. But D equals A over H squared plus K squared plus L squared. We solved for it, and we figured out that it came from 111. All right, so we now know that all these spots are the 111 family of planes. So we want to kind of start assigning positive and negative signs to the numbers. And so there's kind of some rules. You have to have at least one negative value in your numbers here. And this is because we need to satisfy the zone axis criterion. So we have to have at least one negative number in our indexing, or we won't satisfy the zone axis criterion. And again, we'll see it in a little bit. And so I decided just to assign this one as 1, negative 1, 1, 1. So it's a little arbitrary, I know. I was kind of going counterclockwise, and so counterclockwise, instead of having the first one be negative, I made the second one negative and then the third one positive, so I was only assigning one negative number. The rest of these spots are identified by symmetry, and so again, this is a little arbitrary, and I don't want people to be confused, but I made these crosswise spots the opposite of these. Okay, so I arbitrarily picked negative 1, 1, 1 to be this first spot. And sometimes you have to go through and do this again. It may be an iterative process. You have to make sure you're satisfying the zone axis criterion when you do this. And there are, I'll show them later. I'm trying to graphics, I guess. I guess there's a catalog of diffraction patterns for different crystal structures that kind of tell you what the numbers are. And sometimes they have mistakes. And so I'm showing people how to do it. So if you get a table and it has a mistake, hopefully in the future you'll be able to identify it. Okay. I will say there's a lot of computer software that does this. I don't personally do a lot of indexing of TEM diffraction patterns, so I don't have this computer software. At one time I did, I believe. But anyway, I learned how to do it by hand as well, so I'm kind of bestowing that on you all. Anyway, so I started off negative 1, 1, 1. The second one was 1, negative 1, 1. These next ones are going to be the opposites of the first two I indexed. If you think of a Cartesian coordinate, it's like quadrant 1, 2, 3, 4, I believe. So that's kind of how I did it, 1, 2, 3, 4. And so 1, 2, the second one's going to be opposite of 1. This last one's going to be the opposite of quadrant 2. Okay, and hopefully that is clear. Clearer than mud is my goal here. Arbitrarily picked based on the rule that you cannot have all negative. You have to have at least one negative, and you have to satisfy the zone axis criterion. I will tell you that this is I believe this particular one here is the 1, 1, 0 zone axis. I believe I'm correct. Yes. Anyway, we'll get to that in a little bit. So the next question, right? We have other sets of rings, and we actually have 3 sets of rings. So we have the ring made up by this spot, and it's going to have another neighbor over here. I just didn't draw it, and maybe one here and maybe one here as well. And we have another ring. So we have 3 rings that have spots in them. So what about these guys? What about these spots here? Well, we have our friend. We realize that this is the reciprocal lattice vector, okay? The k vector is coming out of the screen for your reference if we want to stay in the vector world. And so we have this one can be found by the vector addition of the 2 adjacent reciprocal lattice vectors. And so -1 plus -1 is -2. 1 plus 1 is 2. 1 plus -1 is 0. So this spot is -2, 2, 0. And don't get thrown off by my poor alignment. I cobbled this together by hand. These next ones are just the next order diffraction spots. So if this was -1, 1, 1, this next one's going to be -2, 2, 2. And this one was -1, 1, -1. This next spot's going to be -2, 2, -2. Okay, so vector addition, and then it's just the next order. So this is the true second order diffraction of this first spot. So again, we had rings. So this is the true second order. This is kind of a second order if you think about it, because it is 2, so it is a second order. So they're both second order diffractions, if you want to look at it that way. All right, so we have our example and of the spots we reflected, or we indexed, excuse me. And so we're trying to figure out the zone axis that these spots came from. And so you can take the cross product or apply the zone axis equation to a combination of spots. And here I'm picking this one, -1, 1, 1, and -2, 2, 0. You can't use any combination of spots. There's some rules. And so you can't use the same order of reflection. And so if I pick 1, 1, 1 here, I can't use 1, 1, -1. And I also cannot use the very next order of the same spot. So if I pick 1, 1, 1 or -1, 1, 1, I can't pick -2, 2, -2, 2, 2. Okay, so I can't use the very next reflection, and I can't use another one in the same order. So I can't use another 1, 1, 1 family to figure out the zone axis. If I pick this one, I can use this one and this one. Okay, so I can use these 3, a combination of these 3. And but again, I can't use the same order. So I can't use another 1, 1, 1, and I can't use this -2, 2, 2. So let's kind of see the next example. I have kind of the truncated version of what I'm going to do. So I picked -1, 1, 1, and -2, 2, 0, and figured out that my zone axis is -2, 2, 0. -2, -2, 0, excuse me. But it's okay to call this zone axis 1, 1, 0 because you can reduce it. So if I multiply everything by -1/2, right, I get 1, 1, 0 basically. So let's take a look at a little bit more in-depth examples. All right, so zone axis now, and it's already kind of worked out in front of us, but I was going to kind of add some notations to kind of clarify it. In this instance, I said this was 1 and this is 2. So H1, K1, L1 is negative 1, 1, 1, and H2, K2, L2, and by this I said negative 2, 2, 0, negative 2, 2, 0. And then you kind of just plug and chug. So I'm kind of trying to make this a little more clear than just the PowerPoint slide. So I kind of feel weird rewriting everything, but I'll kind of quasi do it. And so K1 is 1. So K1 is 1. L2 is 0. And how many highlighters do I have? I have plenty. Okay, L2 is 0. And K2 is 2. And L1 is also 1. And we'll use blue for that one. All right, so one thing I probably need to point out, because I think I mentioned in the previous slide you can use any two spots, but you really can't use any combination of spots. So if I use this one, I can't use this one and I can't use this one, but I can use this one or this one. Okay, but I can't just use any combo. And you'll know you picked the wrong spot if your answer ends up being 0, 0, 0. And so let's kind of work it out again. So we can do, we already did this one. We can do 2, 2, 2, and then I'll do one of these other ones you can't use and show you what you get. So if we're saying H1, K1, L1, and we'll pick negative 1, 1, 1 again. Okay, and H2, K2, L2, and we already did this one. Let's do negative 2, 2, negative 2. And so we'll solve for H. And so K1, L2 equals, so K1 is 1 times L2, and that's negative 2, minus K2, L1. So K2 is 2, L1 is 1. So that's a negative 2 minus 2, and that equals negative 4. All right, so let's go to K. And K is L1, H2. So L1 is 1. H2 is negative 2 minus L2, H1. So L2 is negative 2. H1 is negative 1. And so this ends up being negative 2, again minus 2, and this equals 4. Okay, actually minus 4. And then L, we can look H1, K2, so negative 1 times K2 is 2 minus H2, K1, so H2 is negative 2 times 1. And so this ends up being negative 2 minus 2, which is plus 2, really. And that equals 0. So now we have 4, 4, 0. as our zone axis, but then we can again write this to be 1, 1, 0. Okay, so that's pretty much what we got here before on the previous slide. So now let's take a look at one of the ones I said we can't use. So we can pick 1, 1, 1 again, or negative 1, 1 again. Let's do the next order diffraction. So 2, 2, negative 2, 2, 2. Okay. So one you cannot use. So we said negative 1, 1, 1 is a H1, K1, L1. H2, K2, L2 is negative 2, 2, 2. Let me make it consistent. All right, and so H is K1, L2 is K1, L2 minus K1, L2, yes, minus K2, L1. So K2 is 2, L1 is 1. And so this is 2 minus 2 equals 0. K is L1H2. So L1H2 and minus L2H1. So L2H1. So this is negative 2, and this is plus 2, and that equals to 0. And L is H1K2. So H1 is negative 1, K2 is 2. Oops. H2K1 minus H2 times K1. So I feel like I'm playing bingo. Okay, H2 times K1 is 1. And again, we have minus 2 plus 2 equals 0. All right, so you can't have a zone axis of 0, 0, 0. So the lesson learned here is if 0, 0, 0, you pick the wrong 2 spots. So you pick the wrong combo. And let's kind of go back and look. Let's analyze why it's wrong. So if I pick this one, I can't pick in the same order of diffraction, and I can't pick the very next one. Okay, so I can't pick the second order of the same spot, but I can pick the second order of this spot of the one on the other quadrant, if you will. Okay, but I just can't pick the next adjacent one, and I can't pick the ones in the same order. So that's the ones you can't use. So almost every spot. Hopefully this is helpful. Hopefully this kind of clears up, and I'll fix my kind of previous slide. I've kind of taken a little pause here because I noticed that this is kind of incorrect. The zone axis is a direction, and they're using parentheses in this book, and I won't say where I got this one from because this person swore to me they never made a mistake. But let me just kind of use my laser pointer. So this should actually be direction notation, and it's clearly plane notation. And I was so taken aback, I went and looked up Miller indices again, just to make sure I wasn't lying. But yeah, I was taken aback by this error. Zone axis is a direction, folks, so this should be like a bracket, a hard bracket, and not the parentheses. But anyway, you see tables like this, different books and articles and stuff like that. And so there's kind of these published arrays. There's, again, computer software, and I'll be honest, I'm not that familiar with crystallography computer software. So zone axis criterion, again, defines what spots will reflect due to the relative orientation of the electron beam, so to speak. It's more correct to say orientation of your specimen than the electron beam, but I did say relative orientation. And so this is H from your zone axis times the HKL of your zone axis times the HKL of any of your spots. It has to equal 0. Why does it have to equal 0? Because it's a dot product, basically, and it needs to be perpendicular. And so this is saying a 1, 1, 1 zone axis, and so all these spots, the way they've indexed them, a little bit different than I was showing you all, if you think about it. But still, again, a little bit arbitrary, but it's okay as long as you satisfy your zone axis criterion. And I don't know if I would have indexed this the same way as these folks, but they're 100% correct in saying it's a 660 family of planes if you actually go read this article. So it's actually kind of cool. And again, I answered it already. Why do you think the answer must be 0 for diffraction to occur? Because it's perpendicular. How do you know if your TEM is calibrated? This is a big thing. So this camera constant for this SEM was 4.2 angstrom centimeters, and so that's important because you can plot. This is aluminum, so we have a standard. So we're plotting. Actually, the camera constant isn't 100% that important to do this because you plot your R. Okay, so you know which ring this is, and you plot your R of your measured ring in centimeter versus the HKL, so the square root of HKL. And so let's just say this is 111 and this is something else. And I kind of have to know what rings I'm looking at, which is why you use standards for this kind of thing. If you plot R versus the square root of HKL, or your H squared plus K squared plus L squared, and again, this is a cubic material, so I know I'm looking at FCC aluminum. If I plot it and I get pretty much a straight line, I know my machine is calibrated. So that's kind of the big thing. And I used Excel. I did this actually to calculate how close to a line I had. And anywho, that's how you know if your TEM is calibrated. That's why diffraction patterns are important, because again, this is just a big projection machine. So you should have some linearity between your measured R and H squared plus K squared plus L squared, the presence of where these planes are. Very polycrystalline material, by the way, super nice. Again, just kind of showing an example of using optical microscopy in conjunction with TEM. So these are, again, from the materials I did for hypervelocity impact. So we have this oxygen-free high conductivity copper. It's kind of equiax grained. It has dislocation cells, so dislocation density is pretty high. So we have two things working in favor of hardness and yield strength. So kind of a small grain size relative to this copper, both copper. And we also have dislocation, so we could actually make a modified Hall-Petch equation, that takes into account dislocation density or cell diameter. Here are much fewer dislocations in this material and actually really big grains. So really interesting here. Big difference, see it optically, see it using TEM as well. So kind of summarizing this stuff, so TEM, so current technology has the ability to measure in the sub-angstrom range. We're combining real space imaging with reciprocal lattice information, so we're combining images with diffraction patterns. As I said before, the optics are similar to that of an optical microscope, so we kind of saw that before. It's kind of an inverted biological microscope. High resolution, so advantages, high resolution. You can, and actually high magnification as well. But it doesn't mean anything unless you can resolve 2 points, so you can actually see something. So you can gather crystallographic information as well, and you can actually see small crystallographic features. So namely dislocations, a big deal, stacking faults, twins. Some you can even see rows of atoms. It's really cool. Disadvantages. Sample preparation is probably one of the biggest disadvantages of TEM. It's really, really hard to make a specimen for TEM, and you can read section 4.2 in your book. I've also posted a supplementary TEM sample preparation document, and so you have to make your specimens electron transparent. So thin, they have to be really thin, on the order of 1,000 angstroms, and I say give or take a few hundred, because in some instances you need them to be, kind of more like 600, 700 angstroms, or 60, 70 nanometers. And so give or take a few hundred. The TEM preparation document I posted says between 100 and 150 nanometers. So that's kind of in the range I'm saying here. So 1,000 angstroms, give or take a few hundred, depending on what you're looking at, and also your acceleration voltage. Small sample size, so depending on your instrument, they're roughly 2 to 3 millimeters in diameter, and they're also quite expensive. There's no such thing really as a cheap TEM, and it takes a lot to operate them, actually. So it takes a lot of time and patience. If you're going to do TEM microscopy yourself, I would give yourself a day, the whole day, to look at your specimens. And it's painstaking. This is after you've spent a lot of time making specimens. And anyone who's made specimens for transmission microscopy, whether it's TEM or STEM, can tell you the horror of losing your specimen or damaging your specimen. And sometimes, depending on what you're looking at, the actual beam of your instrument can damage your specimen. It's very heartbreaking. I showed this. So this was my kind of experience making specimens out of metal, extracting a small rod of metal from these small craters, actually. So if you look at the scale bar, it's 2 millimeters. That's not a mistake. And anyway, making specimens that are 3 millimeter, and this is 100 to 200 microns. I think that's close to correct. Maybe not. Oh yeah, because I polish it down further. Yeah, so I do, because we use like a jet polisher, and you'll see in some of the supplementary documents. So there's ion milling, jet polishing, and I was going to share with you, I do microtomy. So I do a lot of transmission microscopy on polymers, and here I kind of have an example of of the microtomes. That's actually a diamond blade, and this was a nice gentleman that came and helped us set up our system. And so that blue thing there at the end of it is a diamond, and the specimen, we're actually trying to get the specimen off of a little chunk of polymer, and the real specimen is right there, that little thing floating around. And he's using, this is called a loop, and he's taking the polymer shavings basically and putting them in some warm water, because we have to freeze it. So we have to freeze it to make the specimen, and then we actually take our specimen and then put it on that little grid I call it a TEM grid. So he took that specimen and then he put it on this grid. And so I do this quite often, actually, for my research. So my specimen is actually smaller than a typical TEM specimen when I'm looking at it. And very small things, very small instruments. I believe this is called just a loop, and very expensive. That little tip there is like $80. And if you break it, it's a sad day, because you have to, shell out another $80 to get another one. And I kind of tried to take this image when he was here, and we get these little shavings, and so this is through a microscope, and you can kind of see it. I have another video somewhere else, and I posted it one time on like Instagram or something of making this. But you get these little polymer shavings. You gather them out of water. So we take them off it's a little pool of a liquid here, and it's dimethyl DMSO. I think it's dimethyl sulfoxone, diluted. We dilute it with water, but we put the DMSO in there, and it's dangerous because DMSO can actually damage your specimen if you're not careful. But it's frozen, diluted. I mean, it's really cold. It's not frozen. It's diluted, and then we gather the specimens and put them on these grids. And here's some example images. And so one time I had access to a nice biological TEM in Arizona, and this is the image that came off of that. Very clear. I'm not actually getting the same clarity on my stem on a SEM. And STEM is scanning transmission electron microscopy, so the beam is rastering. And some TEMs have a STEM mode, and there's also dedicated STEMs. But my SEM on a STEM, two things. So the image isn't quite as clear, and I've actually gotten clear images on my system as well. But this is a biological STEM, and it's running at 100 kilovolts. And so my SEM was running at 30, so I maxed it out. But you notice it's the same material, a little bit different processing for this material, but the contrast mechanism is different on a TEM than a STEM. And so there's pros and cons. So some people swear by stems. Some people, and there are dedicated stems, don't like TEM. They like stems. TEM is always advantageous because you can get electron diffraction. You really can't get electron diffraction on a STEM. If you think about the nature of a moving beam, you're not going to get a diffraction pattern. On a TEM, the beam is static. That's one of the reasons you can get a diffraction pattern. Anyway, the aperture setup on a STEM isn't the same as a TEM either. So there are some differences. And so advantages, disadvantages. The biggest disadvantage I have using my system is that I can look at 12 specimens at a time. So if you look back here, I mean, this is a very tedious process. Even this is a tedious process. And you maybe you'll make 10 specimens and maybe one will be viable that you can actually get a good image off of. And so if I'm using a TEM where I'm putting one specimen in at a time and you have to go through taking your specimen out, cycling the chamber holder to bring it to atmosphere, then go take it back down in the vacuum, it's a lot of time. If you have an instrument like what I have where I can kind of look at 12 at a time, it's a time saver actually. So I can make 10 specimens one day, look at all of them either the same day or the next day. Anyway, kind of rambling on, but there are differences between STEM and TEM. Again, this is basically a projection system. This is actually a little diode, and I might talk about this a little bit more at a later date. So here, there's this blade. This is from RMC. We see the little grids and little things like that. There's a whole set of accoutrements, and I've been promising to kind of say this before, and you can kind of Google these and go check them out yourself. But these are three main places I get my stuff from. So Electron Microscopy Sciences, Ted Pella, or Structured Probe Incorporated. It's hard to say if one's better than the other. I will say, and this is just my personal experience, I'm not endorsing them, and I don't get money from these guys. I give them a lot of money, actually. SPI, I think, in my opinion, sells the best tweezers. I'm just going to say that. And it becomes an important thing when you're dealing with transmission microscopy, whether it's STEM or TEM. Handling the specimens without damaging them is huge. And my favorite tweezers have always come from SPI. Electron Microscopy Sciences, wide range of stuff. Ted Pella, also wide range of stuff. You can get a lot of holders and Hitachi parts, and probably Joel as well, or whatever company you're dealing with, Zeiss, whatever, from Ted Pella. These folks have a lot. I think they have a machine shop, and they have a lot of kind of nice jigs, so you can get like mounts for metallography to put in a SEM and stuff like that. But these are three places I get. Just on a lark, I Googled microscopy supplies when I was making this slide for this lecture, and there's a bunch of others, but these are the three that I use the most, and I will swear that I really love SPI's tweezers. These folks also sell like sputter coaters and stuff like that as well, and I'm pretty sure you can get sputter coaters from EMS as well, probably even Ted Pella. Microtome supplies. EMS was started by Diatome, so Microtomy kind of led to this company kind of coming about. So you can get a lot of Microtome supplies there if that's what you're doing. I'm kind of rambling on, so I think this is a good place to stop. If you have any questions, always feel free to email me. Please take a look at the specimen prep document I've posted. And if you have any questions on what I've done here today, always feel free to ask.
Oh my.
It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.